Hello, and thank you for staying here late in the afternoon. So today I will talk about hydrogen safety. And to be specific, I will be talking about liquid hydrogen safety. So just not to talk in the vacuum, I would like to present some insights from the particular hazards of liquid hydrogen in an airport. Why in an airport? Because that's one of the use cases for liquid hydrogen. You know, some small planes might be able to go on batteries or on compressed hydrogen, but really for long haul, we are talking about liquid hydrogen. And for that, we need to understand not only the liquid hydrogen tanks and all the systems on the planes, but also the refueling operation on the airport, on the ground. So I will talk a little bit about what makes hydrogen special very quickly. I'll talk about who is Gexcon, and I'll finalize with that case study. So why is hydrogen special? Well, you probably know it's extremely buoyant. It rises very, very quickly. However, be careful. We are storing hydrogen, gaseous hydrogen, at very, very high pressures. And that means that although hydrogen is buoyant, a release will go in the direction of that release. It will be momentum driven until you lose the momentum. So it's not true that all hydrogen will always dissipate upwards. It's odorless and non-toxic. In general, a good characteristic. It has a very wide flammability limit. I'll come back to that. It's a very small molecule. We've been talking through the whole summit. It leaks easily. It has a very high laminar burning velocity. What on earth is that term? It just means that an explosion severity will be a lot higher compared to the explosion severity if you had a methane leak or a propane leak. It has a very low ignition energy. It means that it can be ignited very, very easily, much easier than methane or propane cooled. The Joule Thomson effect is a technicality, and something that can be worried is the tendency for high-pressure leaks to auto-ignite. That doesn't mean it's spontaneous ignition. It means that there have been a couple of incidents in the industry where we don't know when the ignition source is. So flammability. So if you can see on the diagram on the left, you see what we call the flammability envelope. That means which combination of hydrogen and air or a hydrocarbon in air will be flammable. You can see for methane it's very narrow, for ethylene it's already wider, for hydrogen it's very, very wide. That means that it's very difficult to keep hydrogen outside of the flammability limit once you have a leak. On the right-hand side, I have a comparison of the minimum ignition energies. That's the minimum energy on electric spark that you need to ignite a mix of hydrogen and air. You can see, just looking at those numbers, that we are an order of magnitude lower than you will have with methane or other hydrocarbons. Even much lower if you compare with Jet A1, if we think at the particular application of aviation. So the ignition sources that you normally will discard with other hydrocarbons, particularly electrostatics, you cannot discard with hydrogen. That's very important if you're putting hydrogen in an environment where you already maybe did a safety assessment and say, well, I have eliminated my ignition sources. You need to think again, have I eliminated the ignition sources that are also relevant for hydrogen? Explosions. I'm not here to scare anyone. I'm just here to give you the facts. Hydrogen, it is more reactive than other molecules. It's a lot more reactive than methane. I already talked about that laminar burning velocity. So if you were to have a leak that ignited, you will have a very violent explosion. That's not to say that you cannot use hydrogen. That is that you need to take all the precautions to avoid that ignition. OK, that's a bit funny, but OK. Moving to liquid hydrogen, as I say. Well, it is very, very cold, 20 Kelvin. It's extremely cold. However, because it's so much colder than the environment, if you were to have a leak either on water or on land, it will expand very, very quickly. The expansion ratio is in the order of 1 to 800. So if you have a liter of liquid hydrogen, you will have suddenly 800 of gaseous hydrogen, and it will happen very quickly. Why did you do that? OK. All gases except helium are solid at liquid hydrogen temperature. Why do we care about that? If you have traces of air or nitrogen or argon in your piping, it will solidify, it will block, and let alone water, of course. It will block valves, it will block vents. So you need to be very careful with that. You need to be extremely dry, extremely clean. You need to sweep with hydrogen before you introduce liquid hydrogen. If not, you will start having solid ice formation. imagine you have liquid hydrogen in an enclosed containment. So you're transporting, like a lot of people here that transport liquid hydrogen in a truck. You need to have proper venting arrangement, because just the normal heat input, you cannot perfectly isolate it. It's just too cold. So even with the best isolation, there will be a slow heat input. It will boil up. Then you will start increasing the pressure in that containment. If you don't have proper venting arrangement, you could have a catastrophic failure. If you were to have liquid hydrogen at ambient pressure, you will go through a phenomenon called cryopumping, meaning it will absorb air, because what happens there condenses on the liquid hydrogen, it reduces the pressure, and it will keep drawing in air, and of course you can cause a very flammable atmosphere. And at the end, the problem is, if you have air in very close contact with the hydrogen, you could have oxygen enrichment. And if I told you that hydrogen in air is very reactive, hydrogen in oxygen is even more reactive. So this is just a small video to show you what could happen if you had a liquid hydrogen tank exposed to a fire. This is an experiment, and this experiment was done in Germany last year. And of course, it was an experiment designed to have an explosion. So we put a diesel fire under that tank. Can you play the video, please? There it goes. Cover your ears. See, that's not a small explosion. That's something you cannot afford to have in an airport or in a place close to, well, close to almost anything. As I say, that's an experiment. That's not an accident. That's something we wanted this to happen in order to understand it, in order to measure it. What precautions do you need to take for a scenario? Well, you need to make sure that that scenario is just not possible, that you cannot have a fire under that tank. Very simple. You don't want to have any diesel or any other liquid fuel stored close to your liquid hydrogen tank where something like that will happen. So, but a lot of people around here will tell me, we have been using hydrogen for decades. That's true. In an industrial application, in a refinery, in a chemical plant, yeah, where people is highly trained, when you have a process safety management framework, where you have an inspection and maintenance regime. Now we're putting it a lot closer to the public. In cars, in some places in domestic applications, in planes, in trains, we're expecting the public to go and refuel their 700 bar hydrogen. It's not the same. Well, you could have a process safety management framework, but you cannot ensure that the public will comply with all those measures. So we, as designers, manufacturers of hydrogen handling equipment, we need to put a lot more layers of protection there to ensure that even if the public doesn't comply with all those safety things, safety placards that we put, it's still safe. For liquid hydrogen, some people here may be familiar with the liquefied natural gas industry. Yes, there's learnings we can talk from the LNG industry, but it's not the same. Liquid hydrogen is a lot colder, and it has different properties. So it's not like, oh, well, we know how to do LNG, we'll just do liquid hydrogen. We need to start to understand what will happen. We cannot keep putting our heads under the sand saying, we'll handle it safely. We need to assume that accidents can happen, leaks can happen. We need to understand what the consequence it is, and then we design for it. We design to mitigate them. And that's where I move. Who is Gexcon? So Gexcon is a process safety consultancy. We have been around for 4 decades, I understand. And we've grown out of the oil and gas industry. We do process safety assessment for all of the industry. But in the last decade, we have put a lot of focus on hydrogen and hydrogen safety. We have participated in a number of experimental research projects, both in-house and with European funding. And we have worked with a lot of clients to help them develop their pioneering applications, being the maritime industry, in the rail industry. So we have developed a lot of expertise through experience, really, because a lot of these things, you have to see them first. It's nothing, you don't necessarily have the textbooks to learn from. So we have done a lot of modeling. You can see some modeling of fires and of dispersions. And we have a lot of expertise across the value chain. We have worked with electrolysis manufacturers. We have worked on storage solutions, on transport, distribution, and increasingly on mobility. So we don't know it all, We are still learning, and that's why we still have a very active research department, but we are learning by experience. We're working together with our clients to help them develop the safest solution we can. So which sort of studies we do, for the ones of you who might not be familiar? So any safe applications start with hazard identification. You cannot mitigate, you cannot control what you don't know. So you need to start, what are the hazards here? And there are several methods to it. In the process industry, it's very common to do what we call a hazard identification workshop. And then we move through more specific type of studies to try to identify particular scenarios. Where can it go wrong? Where do we believe it can really go wrong? And what can happen? And then you move, well, OK, I don't like that leak. I don't like that possibility of an explosion. What can I do about it? And then you can do what we call a layer of protection analysis, or a LOPA, when you say, well, I will start with, of course, sound process design, and I will put process control, and I will put detection and mitigation, all those things that to reduce the likelihood of a leak becoming an explosion. We also do a lot of consequence analysis. We have our proprietary software, both simple tools and computational fluid dynamic tools that allow us to understand in detail what will happen in case of a leak, because as I'm going to show you in a minute, it's not the same having a leak, for argument, here, that over there when there's a lot of stands. What will happen if that leak became a fire, or in which situations you will have an explosion. And finally, a lot of like, well, why do I care if I have an explosion of 300 millibar or 500 millibar? That doesn't tell me anything. I want to know whether I will destroy the building, whether I will kill someone, whether I will have doors flying. And that's where we can do a structural response. So as I've been saying, we have several pillars in our company. We offer our proprietary software in the form of Flax CFD, which is our flagship tools. And we also have analytical tools that are a lot easier to use, called effects and risk curves. We also offer consulting. We have offices all over the world where we can work together with clients to help you devise exactly the safe solutions you need. We do testing. So if you have an equipment and you want to say, how will this equipment respond in case of a fire? Is this passive fire protection effective? Things like that we can do in our site in Norway. And we also offer a lot of training. And in particular, we have developed a hydrogen safety training to offer to companies where they have felt the need to increase their awareness. So now the fun part. So talking to some people in the industry, it seemed to me that the aviation companies were doing a very good job of looking at their hydrogen tanks and all the components, making sure that plane was safe flying on liquid hydrogen. But it seemed to me that no one was looking necessarily at the interfaces. And that's what I've learned working in this hydrogen environment. There's a lot of players. There's a hydrogen manufacturer, there's the compressors, there's the storage, and there's not necessarily the same company managing all that. And that leads to a lot of interfaces, and experience in the industry shows that the interfaces when things go wrong. So that's why we decided to do this little study about what will happen if you were refueling a plane in an airport and things went wrong. So what questions did we ask ourselves? Can we have a liquid hydrogen plane? Can we refuel a liquid hydrogen plane next to a conventional kerosene plane, as we do now? Or do we need to put a hub away from everything, at least until we understand enough the characteristics of liquid hydrogen? Can we, I mean, probably a lot of you have been in a plane where the pilot tells you, oh, please do not hook up your safety belts because we are refueling. Can we do that with a hydrogen plane? Or do we need a safety perimeter? So while refueling, we'll do this in an automated application, and no one is around it. We don't know which sort of equipment is required. Does the inspection and maintenance that we have in place is enough, is sufficient, is adequate for liquid hydrogen? And of course, people will, leaks will happen. What do? We are not going to handle them the same as a kerosene leak. Kerosene will form a nice pool. You will avoid sources of ignition. The fire services know what to do with a kerosene leak. We have been approached by certain emergency services, like, well, we will know what to do in case of a liquid hydrogen leak. So That's where we started playing with this. So that's just a model. We created a plane. And by looking at the open literature, we know that the airlines plan to put the liquid hydrogen tanks at the back and ideally refuel it in a conventional way, so with a truck full of liquid hydrogen that come next to the plane. So you can see there, we decided to put 2 leaks. We assume that the hose will be high reliability, the hose itself won't fail, but experience in the industry tells you that leaks happen at connection points. So it can leak where we connect it to the plane or where we connect it to the truck. And then we made certain assumptions about the state of the liquid hydrogen, and then we went and played with it. The advantage is you can run a large number of simulations in the computer, and then you can try to understand what happens. So, oh, there it's running. So what you can see there, we assume a leak under the plane, and you can see there all the color contours there tell you the different concentrations of hydrogen. So where you see those pink colors is very, very high concentration, close to the release point, and then it starts mixing with air, the concentration decreases. Now, one thing I didn't mention before is that the severity of a hydrogen explosion is very highly dependent on its concentration. So it's not the same to ignite a leak of hydrogen at around 4 or 5% than a leak of hydrogen at 20% hydrogen in air. So we don't only have to worry about where is that hydrogen, but also about the concentration, and that's what this type of model tells you. So if I play it again, you can see how that leak develops. Now, an important thing to notice with this particular simulation is that the cloud, the flammable cloud of hydrogen, covers where that little baggage cart is. Now, of course, that's a model. We put the cart there, but it is a realistic position. It can be close to the plane. So there's places where people will be. Is there such a thing as an ATEX baggage cart? I doubt it. So that's already immediately a source of ignition. Do we want to expose people to that particular scenario? Remember, liquid hydrogen is very cold, and even if it already mixed with air, it's still very cold. So you could be exposing people to a very cold environment. Now, we did a couple of scenarios like that and just showing 2, but this is just to show that you can create a fairly big flammable cloud that will affect a large area of that airport where it can easily form a flammable cloud. Now, we safety engineers like to ignite things. We just like bangs, we just like bombs. So that's what we did in the computer. And that's what you can get, a nice fireball. Now, you can see the fireball is transient. It's not something that lasts for a long time. But whoever is caught inside that fireball will be a fatality. So again, you can see that if you had people boarding the plane or if you had people loading the baggage, you will have several fatalities there. So it is very clear that this is a scenario we cannot tolerate. Now, the other thing we worry about is you've all been in one of those modern airports that are full of glass, which is great for the people. You can see your plane. It looks nice. However, if you have a scenario like that, apart from the fireball that you're seeing there, you also create overpressure. That overpressure can break those windows. You don't need a lot of overpressure to break windows. So if you had that scenario, and again, let me be clear, that's a scenario that we thought of. It's not something that had happened, not something that necessarily we expect to happen. It's just an example of what could happen. But in that case, you could create enough overpressure to break all that glass and to cause injuries of people in the terminal. So then you ask the question, well, what will we do now? You know, do we need to refuel those planes really far away from the terminal? Do we need to evacuate the area around the refueling plane? The answer is we don't know, but in my opinion, what we need to do is start having that conversation. It's, okay, the liquid hydrogen planes are coming, or at least that there are signs that they are coming. We need to have that conversation between airport, airlines, equipment manufacturers, and safety companies to see how do we make sure we can do this safely. Again, the aviation industry has a very good safety record. They know how to do things safely, but hydrogen is different. They haven't handled it before. You know, they can handle kerosene safely, but they just need to change their protocols. They need to change their understanding. And it is really important to start looking at it now, to start putting their process safety management in place since the concept stage. Because once they have designed the system, it is too late and it will be very expensive to change. Again, I mean, I show you those pictures. I know they are spectacular, but it's not to scare people. It's not to say it cannot be done. It is to say you need to think about it. You need to put your safety systems in place. You need to put your operational protocol in place to make sure you can do it safely. I hope I show you that you can use some consequence modeling tools to try to understand those risks. This was a very, very, very quick exercise. Of course, it requires a much lengthier and much more in-depth exercise to really understand how will you handle hydrogen in an airport. But I think now is the time to act. You know, there's no point waiting until Airbus or one of them has the perfect hydrogen plane. When they try to refuel it, it's like, oh my God, how do we do this? Will the authorities allow it, for example? So yeah, thank you very much for your attention. If you have any questions, I'm here. A concrete bunker, okay. So you mean having a special place where you will refuel your plane?
Where you store your hydrogen.
All right, you're looking at the storage. Okay. No, we haven't in this particular case. It is a possibility. It's just we need to be careful with bunkers because, of course, a bunker creates confinement. And one of the things that make an explosion worse is confinement. So in the ideal situation, you want to have things in the open, certainly large amounts, so they can dissipate that the wind, the normal atmosphere, the normal turbulence in the atmosphere helps you dissipate that hydrogen. There might be situations where putting a safety wall or something to protect the public is the right application. But again, you need to study it. I cannot stand here and tell you that's the right solution because it will depend what do you have around it. What are you trying to protect and what else can happen?
Okay, of course, the airline industry has good record and so on. But if we are trying, to look to various industries and mobility and so on, then, the chances are not that great that something will happen. Because that's the way it is. I compared this to the nuclear industry some time ago.
Yep.
The nuclear industry were confined to the nuclear plants. And there were the design, there was all the measures and so on. That is something, that can be compared to aviation.
Yeah.
Here. But if you go to industrial and or mobility, then it's not that. The comparison is not applicable anymore. And the chances of something can go wrong is much higher.
Exactly. Exactly, because that's what I mentioned in the beginning, is putting things very close to the public.
For me, as I think about it, if we look to natural gas applications at home, I doubt very much that will be any hydrogen applications at home.
I agree with you. I personally agree with you. But governments are pushing in that direction, so I think it's our role to tell them that might not be the best application. Okay, thank you very much.